Well, hello, welcome again to Math 315. This is the second recording for Chapter 9 or Section 9 on the real numbers. And we've been talking about the supremum of a set and the infimum of a set of real numbers. And I did a couple of examples of those in the previous recording. Here's another interesting example here. We let A be the set of all rational numbers. So Q stands for the set of rational numbers whose square is less than 2. So for example, 1 would belong to this set. 1 squared is 1, which is less than 2. And again, we can sort of think about this on the line here, and we'll draw an interval here. This is going to be all the numbers that are whose square is less than 2. It's going to look something like this. Now, if we're only in the rational numbers, if the only numbers we knew about completely were rational numbers, then this set does not have a supremum. If the only numbers we know about are the rational numbers, then this does not have a supremum. On the other hand, if we allow real numbers, all the real numbers on the line, then the set of all rational numbers whose square is less than 2, that set does have a supremum, and the supremum of that set will be equal to root 2. The supremum of that set will be root 2 because root 2 is belongs to the set of real numbers. So this is an important example. It gives us the key difference between the rationals and the reals. If I'm working in the rational numbers, then I can write down a bounded set that has no supremum. In the real numbers, if I write down a bounded set, then it will have a supremum. So I'll come back to that fairly shortly when we look at this axiom of the real numbers. So we can also extend this concept of supremum and infimum to functions over some set B. So the supremum of f of x is the sup of f of x where x belongs to B, and the inf of a function is the infimum of f of x where x belongs to B. And probably good to have a look at an example of one of these. So here's my function, and my set B is going to be the set of real numbers. So we're going to, with f of x is 1 on 1 plus x squared. We want to find the supremum of f of x, where x is real, and the infimum of f of x if x belongs to the real numbers. And so here's the solution to this. And we do this basically just by drawing a picture. So I'm going to draw the graph of 1 on 1 plus x squared. You can see it's an even function. If you replace x with minus x, doesn't do any damage. Put x as 0, it's going through 1. It's going to be smaller than 1. And as x goes to infinity, it's going off to 0 both sides. So either you just draw this from common sense, or at worst you can get a computer to draw a sketch of it. So we're looking for the biggest this can be. We're looking for a number which is a bound on all of these y values. And of course the biggest one is going to be 1. So the supremum of f of x is 1. Now in this case, this is also equal to the maximum of f of x. So in this case it happens to equal to the maximum of f of x for x is in the real numbers. Sometimes the supremum equals the maximum. Sometimes there's no maximum, but there is a supremum. On the other hand, the infimum is, I want to know what number are all of these y values on the y-axis, or the f-axis if you like. What number are all of these numbers bigger than? And the answer is 0. This never gets to 0, but it gets as close as you like to 0. So the infimum this time, so this function has no minimum. It has no minimum, but it does have an infimum, and the infimum is 0 as I move through the real numbers. So the following statement then can be taken as an axiom which the real number system needs to obey. So So as we saw above, it distinguishes the real numbers from the rational numbers. So here's our axiom. An axiom is a statement that we take as given. We just believe it. You can't prove it. It is simply a statement that we take as a given rule. So we let A be any non-empty subset of the real numbers that is bounded above. So again, think of intervals. You've got some interval and it's got some bound on it. Then the supremum of that set is a real number. That is the axiom. This is not true for rational numbers. We saw up here was a set A, which was certainly bounded above. It's bounded above, if you like, by 2. All the numbers in this set are less than 2, or 3 for that matter. So it's bounded, but in the rational numbers there's no infimum. But in the real numbers there is. And that's the thing, that the axiom that distinguishes rational numbers from real numbers. Every non-empty subset which is bounded above has a supremum. Well, just a little theorem here, 8.1. If we've got two functions f and g defined on some subset A of real numbers, then the supremum of f of x plus g of x, if I add the two functions together and take the sup, then that's less or equal to the sup of x plus the sup of g. And just a little proof of this here. So if we take m to be the sup of f, n to be the sup of g, then what does that mean? That means that f of x is less or equal to m, and if g is the sup, if n is the sup of g, then g of x is less or equal to n for all x in A. Well, then if I add these two inequalities, I get f plus g is less or equal to m plus n, and that's true for all x in A, and that's the definition for this to be the supremum. So take the sup of both sides. The sup of this thing is less or equal to m, which is the sup of f, and n, which is the sup of g. So just a very simple statement there that you can add two functions. The supremum of the sum is less or equal to the sum of the supremum. Now I mentioned before this idea of Dedekind cuts, and this sort of fits in a little bit with what we're doing here with supremum and so on. So Dedekind cuts, we say that a non-empty proper subset of the rationals, Q, is called a Dedekind cut. Now for Dedekind cuts, think of them as open unbounded to the left intervals. So we think of a Dedekind cut as this set, I'm going to write it as little x, which is less or equal to some number here. So this set is called a Dedekind cut if, whenever I take a q inside this set x, so there's a q, if L is less than q, then L also belongs to x. This is a complicated definition to get your head around, but this is what it is. So a Dedekind cut, just think of it as an open half interval here going back forever. It says it's a Dedekind cut if I take any q inside the cut, I take a number L that's less than it, then L also has to belong to x. That simply means that this goes back forever. X has no maximum. That is, if I give you any q inside here, then there is some number r which is also still inside the set, so that q is less than r. In other words, this set has no maximum, but of course it will have a supremum. And the supremum is going to be, if we think of this point here as A, so we're really thinking intuitively of this set X as being the open interval minus infinity up to A for some A. So a Dedekind cut is one which has, it's a set, think of it as an open interval, it's got no maximum, it contains all the numbers from here backwards, and such an object is called a Dedekind cut. And what we're going to do, of course, we're going to identify every real number by the supremum of this set X. Now, it is possible to define the sum, the difference, the product and quotient of two Dedekind cuts, but I'm not going to go into all the technical detail here. I'm not going to do much more with this except to say that this is one way of defining the real numbers. You simply take the set of all Dedekind cuts and you define the real numbers by the supremum of each of these Dedekind cuts. And that's another way of constructing the real numbers using this idea of supremum. So the set of all cuts is then identified with the real numbers. And we can say that the supremum of each of the set gets identified with the corresponding real number. So in the rationals, we can define a notion of less than by how do we decide when one fraction's less than another? Well, it means that this fraction minus this fraction is negative. And if I put these over a common denominator, it's the same as saying PS minus RQ is negative. And this now is a statement about integers. So we can define the notion of less than in the set of fractions by replacing it with a notion of involving just integers. And in the tutorial problems, you'll do one of those. Now we can use Dedekind cuts then to make sense of less than in the real numbers. So in the reals, we can define the notion of less than by saying that the real number x is less than y if the Dedekind cut x is properly contained in the Dedekind cut of y. In other words, if we think of a picture here, if we're saying x is less than y, so we take this as our Dedekind cut x, and we take this as our Dedekind cut y, and so we say x is less than y if this set's contained inside this set. So we can carry across this idea of being able to compare or to order the real numbers. Now, I said I'd go through all the axioms. You don't need to remember any of the axioms, but I'll just go through them because I want you to see how this works. So it can be shown that Dedekind cuts, i.e. real numbers, satisfy the following long list of axioms, and you can also take these axioms as defining the real numbers, but as I mentioned before, there are issues here then about consistency and uniqueness. So suppose A is a set. Then we need the real numbers have to satisfy the following axioms. Firstly, these are called the field axioms. If you've done a little bit of algebra, abstract algebra, you will have come across fields, and these are just the axioms for a field. Firstly, if we take two objects in A, we have to be able to add them and stay inside the set. We have to be able to multiply them in some way and stay inside the set. The second field axiom, we've got two objects in the set, then the order in which we add them doesn't matter. A plus B is B plus A. The order in which we multiply them doesn't matter. A times B is B times A. Thirdly, if we take three objects in the set, then we can the order in which we add them again doesn't matter. That is, we have a associative law. If you add A plus B first and then add on C, you get the same as if you add B and C first and then add on A. And similarly with the multiplication, if you multiply A and B first and then multiply by C, it's the same as if you multiply B times C and then multiply by A later. These are all, in some sense, sort of motherhood statements. They're all things that you really would love to be true and are true in most of the structures you've seen, but there are sets of objects where these things are not necessarily true. And you will have come across those if you do a course in abstract algebra. So there is an element 0, which we call the zero element, that if you add 0 to anything, it doesn't change. there is a minus, for each a in A there is an element we call minus A, so that if I add A to minus A I get the 0 element. There is an element 1 called the identity element. If you multiply 1 times A you get A. Now what makes it up to here, this makes it what is called a commutative ring. Now to make it into a field we have this axiom here that says for each A in A except for the 0 element there is an element we call A inverse, so that A times A inverse gives you this unit element, this identity element 1. And axiom 8 says we have a distributive law. We can if we've got A times B plus C, it's the same as multiplying A times B and then add A times C. That's our distributive law. Now up to here, any set which satisfies these axioms is called a field. The set of rational numbers is an example of a field. The set of integers is not a field, because if I give you, say, the number 2, then 1 over 2 is not a whole number. So there's no multiplicative inverse there. Now the second group of axioms are called the order axioms, and they simply say that we can order the elements of this set. Now there are sets where you can't order the elements. The complex numbers, for example, you can't order them. You can't say 1 plus I is less than 1 minus I or something. It doesn't make sense. The order axioms are important in the real numbers. So it says there is some relation we call less than on the set A, such that if I give you any two elements of A, exactly one of the following statements is true. The two numbers are either equal, A is less than B, or B is less than A. Exactly one of those three must be true for any pair of numbers A and B. If I give you three numbers in the set, then we have what's called transitivity. That is, if A is less than B and B is less than C, then A is less than C. If I give you three numbers in the set with A less than B, then I can add C to both sides and nothing goes wrong. And finally, if I give you three objects in the set and I give you C is bigger than 0 and A is less than B, then you can multiply both sides by a positive number and it doesn't affect the inequality sign. Now, up to here, a set which satisfies these axioms is called an ordered field. Now, there are fields which are not ordered, like the complex numbers, for example. Again, the set of rationals is an example of an ordered field. But there's one more axiom called the least upper bound axiom, which we've met a minute ago, which is the one that distinguishes the real numbers from the rational numbers. It says for every non-empty set S of A, which has an upper bound, so if there's an upper bound, if it's bounded above, then that set also has a least upper bound which belongs to A. That's another way of saying that the supremum of any set A, so I'll write that in a slightly different way, so i.e. the supremum of our set of our set S, the supremum of our set S actually belongs to the set A. And it's that axioms I mentioned before that distinguishes the rational numbers from the real numbers. All the other properties of real numbers, any other statement you can make about the real numbers, can be derived from these axioms. And we're not going to do too much of that, but all the other properties of real numbers can be derived or constructed from this, from these axioms. And that will be the end for this particular recording.